Imagine you have a full bucket of water. If you leave that bucket out in the sun, it's going to take days, maybe even weeks to evaporate. But if you take that exact same amount of water and dump it across a hot driveway on a summer afternoon, it completely dries up in mere minutes. The physics here are straightforward. In a deep bucket, only the top surface touches the air, while the water underneath stays cool and insulated. When you spread the liquid out, almost every single drop is directly exposed to the heat all at once. If we drop a single bead of water onto a severely heated cast iron skillet, it flashes into steam the instant it touches the metal. When you combine a paper-thin layer of liquid with high heat, evaporation happens almost immediately. And we can use that exact physical reaction to solve a major problem in manufacturing. Factories produce thousands of gallons of concentrated wastewater, salty brines, and thick syrups every day. They need to separate the solid waste from the water, but they can't afford to let it sit in giant vats and slowly boil away over several days. To do this quickly, they use a machine called an Agitated Thin Film Dryer, or ATFD. Instead of waiting for a vat to boil, the ATFD acts like a continuous, massive version of that hot skillet, separating thick industrial sludge into pure water and solid powder in a matter of seconds. Let's look inside to see how it works. This cross-sectional diagram shows the basic structure of the ATFD. It's essentially a tall metal cylinder with a hollow interior chamber, surrounded by an outer shell called a heating jacket. In the first step, hot steam or specialized thermal oil is pumped into the outer jacket. This turns the entire inner wall of the central chamber into a searing hot surface. Next, the factory pumps its concentrated feed, like a thick, salty wastewater, through a nozzle at the very top of the machine. If we stop here and let gravity do the work, we have a problem. The thick liquid will simply pour down, clump together, and burn right onto the hot inner wall, completely ruining the process. Applying extreme heat is easy, but if you don't have a way to control exactly how thick that liquid is when it touches the wall, the entire system clogs and fails. To fix this, we have to look at the machine from a top-down view. This diagram shows a central rotor positioned inside the cylinder. Attached to this rotor are long wiper blades that spin rapidly, reaching out to just barely skim the heated wall. As the thick liquid drops in from the top, those high-speed blades catch it. They smash the liquid against the hot wall, smearing it into an ultra-thin layer, usually just 1 or 2 millimeters thick. Because the blades are constantly wiping the surface, the liquid never stays still long enough to burn or form a hard crust. Now we have our hot skillet effect. That 1 millimeter layer of water hits the searing metal and instantly flashes into steam. The vapor rises up and exits through a pipe at the top, heading to a condenser where it cools back into clean, pure water. With the water gone, all that's left is the solid salt powder. Gravity, combined with the downward angle of the spinning blades, pushes this dry powder down the walls until it drops out of a chute at the bottom. By adding mechanical wiper blades, the machine forces the liquid into a paper-thin film. What would normally be a slow, messy boil becomes a near-instant, clean separation of water and solid waste. To see the actual scale of this operation, let's look at this flowchart mapping a standard test run. We start by feeding exactly 1,000 liters of salty sludge into the ATFD. Lab reports show this sludge has a 30. If we do the basic math, 30% of that 1,000-liter batch means we should theoretically extract exactly 300 kilograms of perfectly dry salt. Subtracting that solid mass from our starting volume leaves us with exactly 700 liters of pure, evaporated water escaping out the top. But in real-world industrial conditions, no machine is perfectly efficient. As the salt drops out of the bottom, it acts like a sponge, trapping a small amount of moisture inside. So the true output looks slightly different. Out of the top, the factory recovers roughly 670 to 680 liters of clear, reusable water. Out of the bottom, they collect 320 to 330 kilograms of slightly damp salt. By forcing heavy sludge into a microscopic layer against a hot spinning wall, the ATFD achieves predictable, massive-scale material recovery. It proves that sometimes spreading yourself thin is exactly how you solve the biggest problems.